Welcome! In this video I'll go through the normal mode equation, and this is a way of simplifying the ideal MHD equations to a single equation for the displacement. And this is the first item, so we'll look at the psi, it's called, the displacement of the plasma, and then we'll show that this can be used to prove some properties of ideal MHD, and particularly that the frequency squared is real, and this means that the waves are either oscillating when the frequency is real, or they're growing unstable, which is when they're imaginary. And so you don't, in ideal MHD, you don't get waves which are oscillating and growing at the same time, and those occur in non-ideal equations, but not in ideal MHD. And then we'll also show that this proves also that the different oscillation waves in ideal MHD are orthogonal, which means that the different oscillations don't couple together. And so you can look at a single mode and understand how it behaves without considering how they all join together. So we're going to take the ideal MHD equations, the linearized versions, which is where we've assumed some kind of small perturbation around a background, and so all the quantities, like the density, for example, has become a background density plus a perturbation, and the same for all fields. We're going to assume here that U0 equals 0, so it's a stationary equilibrium. So there's no equilibrium flow. I'm going to also assume it's in force balance, so we have J0 cross B0 is grad P0. So it's the equilibrium force balance. And then we can write the perturbed quantities, so these perturbed small perturbed quantities, and these are the equilibrium quantities. And then we're going to write the ideal MHD linearized equations. I'll just write them out here because we derived them in a previous video. So these are linear equations for these perturbations in density, pressure, velocity, and magnetic field, and they all depend linearly on this perturbation size. So each term in this equation just has a single perturbed quantity. Here, delta U's, and delta P's, and delta B's. And so together, this is a linearized equation, but in 4 variables. In total, there are 8 unknowns. So there are 3 components of velocity and 3 components of magnetic field. What we're going to show here is that we can simplify this whole thing into a single equation, and the way to do that is by considering the displacement. This is how much the plasma has moved from its starting location. So we're going to write this as psi, and it's some function of space and time, and it's how far the plasma has moved. So if the plasma starts this is some kind of spatial coordinate, and the plasma moves to here, then this is the displacement. And it changes at different points. So psi is some function of space because at different locations the plasma is moving in different directions, and the plasma, as the plasma is moving, displacement is changing, and so the velocity delta U is just the rate of change of the displacement with time. So it's the rate of change of psi with time gives us the perturbed velocity. And so this is the movement of the plasma from the equilibrium case. This straight line here would be the equilibrium, then the plasma is displaced, is moved by a perturbed flow. Okay, we can use this to essentially integrate all these equations in time. So we now integrate this in time, and it just becomes delta rho. If we integrate this second part in time, so I'll write this here. So if you integrate this in time, integrate this whole thing in time, you integrate this right hand side in time. So this part here will just become, so we have a minus, and here this is a u, so it's a d psi by dt, and then this gradient doesn't depend on time, and so this, when integrated in time, this will just become minus psi dot grad rho naught, and the same for this part here will just become minus rho naught gradient of psi. And so all these equations, we can do the similar thing. We can just get the equation for delta rho in terms of displacement. The pressure equation is basically the same. We get a perturbed pressure in terms of displacement, and the same for the magnetic field. So I'll write them out here and see them. So what we can do now is take these equations for the perturbed quantities rho, p, and b, and substitute them into the momentum equation. So we can just take this equation here for the rate of change of the velocity, and so this is just the second derivative of psi, and we substitute all the equations for these. So here we have the delta p, we have the delta b's here, and we're just going to substitute in from the equations we just derived, and so we'll end up with an equation which is the second derivative of psi on the left hand side, and then an equation for terms involving psi on the right hand side. So we just get a second derivative of psi that just comes from derivative du by dt, and then on the right side we have, so with this equation for the momentum, so I put the rho naught on the left hand side to make this the momentum, or the rate of change of momentum, and this is the force per volume on the plasma. So here it's just left as delta p's and delta b's. We can, if you like, substitute in the expressions, and you end up with this is delta p, and then these are the delta b's substituted in here. You see it's quite a complicated partial differential equation, but it's all linear, so there's the only terms that vary are this psi, and this whole thing is just a function of psi, of the displacement, and this is the force operator. And so we now have a linear equation where the second derivative of psi in time is some linear function of psi. And so it's a linear function. And so you can write that psi is psi hat, which is just a function of space, multiplied by e to the minus I omega t, where omega here is the frequency. And so the second derivative of psi, you just have a minus omega squared factor, and so you can write that, and this is the normal mode formula, or normal mode formulation of ideal MHD. So this is a simple way of condensing all these ideal MHD equations into a single equation. We can then use this to analyze properties of linear MHD waves. So there are a few nice properties of this operator, and what this relies on is that this force operator is self-adjoint, and this means that the integral of some function, which we call eta hat here, which is some function of space, times the force operator on a different function psi, which is also a function of space, and this integrated over all space is equal to, now if I swap these around, so if I put the psi on the outside and the eta on the inside, so this means that it's self-adjoint. It has this property. Proving that takes quite a long time, and it's fairly straightforward, but just quite long. Essentially, you substitute these into the operator above, and then quite a long calculation later. You can see it's quite a large expression here. But now here we can use this property to see what that means for the waves. And so the first one is that we see that omega squared is real. And to see this, what we do is we take the normal mode formulation, so we take this equation up here, and we first multiply it by psi star. So if I take this equation here, so multiply this equation by the complex conjugate of psi, and what we're going to get is we have a minus rho naught squared. And now here we get a mod psi squared, and we get a psi star. Okay, and then we can do the same thing, but take the complex conjugate of this equation here, and then multiply through by psi. So we have so minus rho naught. Now we have omega squared complex conjugate, and now if we write out the equation, so we have psi star, so the complex conjugate of psi is the force on psi star. So I'm just taking the complex conjugate of this equation, and I multiply through now by psi. So I have these two equations, A and B, and now I can integrate them both, and I can just write down that we have so rho naught and omega squared. Well, omega squared is a constant here; it's just the eigenvalue. And so we have minus omega squared, then the integral over the volume of rho naught times the mod squared of that over the whole space. So that's equation A. And that's integration over all space here. And then the similar for equation B, so we just end up with equation B gives us minus, now we have an omega squared complex conjugate because this is self-adjoint, you can see that these two equations are the same because it's self-adjoint. And therefore, what we must have is that the omega squared here must be equal to omega squared star. And so therefore omega squared is real. And so what this means is either waves are growing or they're oscillating. And this makes finding marginal stability, so the limits where a wave becomes unstable or goes from stable to unstable, is quite easy to find, because it's just when omega squared is equal to 0. And in general, this is not necessarily true for non-ideal equations. There can be waves which are growing and oscillating, and so finding marginal stability is much more difficult, because then you just need to consider the imaginary component of omega. So omega might have a real and imaginary components, and so the boundary between what's stable and what's unstable can become more difficult to find. But ideal MHD is quite straightforward. Okay, the other property I want to look at is the orthogonality of the modes. And here we can think about if we have two different modes. So if we have one mode where we have a frequency of omega n, for example, and here we have a psi is some f of psi. Then we have a different mode. We have another mode where we have omega m squared, for example. This is a different mode. We have some different function. So we found two different modes of the system, and they have different frequencies, omega n and omega m. Again, we can write out how this works by multiplying this equation through by eta, and this equation through by psi. And so we end up with minus rho naught and again we integrate over all space, and we end up with, and because this is self-adjoint, again this side, the left hand side here is the same as this here, and so and we have that this must be equal to this, and so we rearrange this to write down that we have on the left hand side, so omega n, say, minus omega m, to move one of them over to the other side, multiplied by this integral rho naught eta dot psi. So integrate over all space must be equal to 0, because this part this must be equal to that, so this side here must be equal to that over there, and so either omega n is equal to omega m, or this is equal to 0, and so therefore if omega n is not equal to omega m, then they must have the integral of this rho naught eta dot psi x equals 0. And so if rho naught is a constant, then these modes are orthogonal. The other way that this can occur, of course, is if they're degenerate. So if omega n is equal to omega m, then these modes can couple together.